Hi everyone, my name is Claudia Kemp and this is Module 4, Chapter 11. So number 1 gives a situation in which two students are asked to reflect this block pattern here. They did this. We are asked to respond and we're asked to say what type of motion they used. So the students used a 180-degree rotation motion. Some of you may have forgotten, or maybe you're wondering, what is 180 degrees? Well, if we use this handy-dandy protractor right here, let me move my face 1 second. Okay, we use this protractor right here. We can see that A is at point 0 and B is at point 180. Therefore, anything that goes from point A to point B is 180 degrees. As you can see here, the green triangles here went from point A to point B, 180-degree rotation. Number 2 asks that we identify figures with different symmetries. Part A asks for shapes that have one line of symmetry and no rotational symmetry. First of all, we need to know what those things mean. First of all, a line of symmetry, we're going to use a basketball court. The half-court line would be a line of symmetry, because a line of symmetry is anything in which the shape looks the exact same on either side. So a half-court line, the shape mirrors itself on either side. A rotational symmetry, we're going to use a star. A rotational symmetry is any shape that can be rotated under 360 degrees and look the same. A star can be rotated a bunch of different times and look the same. So we have these shapes here, and we are asked to determine which ones have one line of symmetry and no rotational symmetry. So the first shape has one line of symmetry, but it also has another one. Same goes for the second shape and the third shape. Now the fourth shape only has one line of symmetry, but we have to know if it has rotational symmetry or not. The first shape, there's a couple times it rotates that it can be the same. Same goes for the second and the third, the square and the rectangle. The fourth shape, however, has to make a 360-degree rotation before it looks the same. Therefore, it has no rotational symmetry. Part B asks that we find a shape that has no line of symmetry and rotational symmetry. So the first shape has rotational symmetry. The second shape has rotational symmetry. We already know that squares do. The fourth shape, not really. It doesn't really have rotational symmetry. But which ones have no line of symmetry? Well, the diamond has 2, and we already know a square has 2. The fourth one doesn't have any. So the first shape has no line of symmetry, but it does have rotational symmetry. Part C we want a shape that has one line of symmetry and rotational symmetry. So just one line, but it rotates as well. So the first shape has 2 lines of symmetry. The second shape does 2. The third shape even has 2 lines of symmetry. The fourth shape, however, doesn't have any line of symmetry. So it's really not possible, at least with these 4 shapes, in order to have one line of symmetry and rotational symmetry. Number 3 gives a situation in which a student cuts out a regular pentagon, a hexagon, and an octagon like this, and she thinks that it's a vertex figure and we are to respond to her. Well, first thing you've got to know is that a vertex figure is determined by whether or not the sum of the interior angles equals 360 degrees. That's why there's no gaps or overlap. We have to find the sum of the interior angles of this shape here. So in order to determine the measure of interior angles of a polygon, you take the number of sides minus 2 and multiply that number by 180. We will start with the pentagon here. So the number of sides for pentagon is 5. 5 minus 2 times 180 is 540. Divide that by each angle so that we know what each angle is. And so we divide that by 5, and we get that each angle is 108 degrees. Moving on to the hexagon, which is 6 sides. 6 minus 2 times 180 is 720. Divide that by 6, and we get that each angle is 120 degrees. Moving on to the octagon. 8 minus 2 times 180 is 1080. 1080 divided by 8 is 135 degrees. So each angle of an octagon is 135 degrees. But we want to know if this is a vertex figure. So we're going to look at these angles here to see if they equal 360 degrees. So we take one hexagon angle, which is 120, one pentagon angle, which is 108, and one octagon angle, which is 135, and we get 363 degrees. Therefore, it is not a vertex figure. Number 4 wants us to demonstrate relationships within a figure. This figure, actually. So part A asks, is triangle QPT congruent with triangle SPT? So we have triangle QPT here and triangle SPT here. We want to know if they're congruent. So we will use what is called side-side-side property of congruency. And it states that if 3 sides of one triangle are congruent with the sides of another triangle, then the 2 triangles are congruent. Well, we can see that line PT is the same as itself, and it's the same line in both triangles, and since the line QM is also the same, then we know that the 2 triangles are congruent. Part B asks, is angle QPT congruent with angle SPT? Well, we would use the corresponding angles. Okay, so since these 2 angles are corresponding angles within what we already know are corresponding triangles, then the 2 angles are congruent. Part C asks, is triangle QPV congruent with triangle SPV? And in this case, we would use side angle side property, which states that if any pair of corresponding sides and their included angle are equal, then the triangles are congruent. Well, the angle that is in QPV, that is the one that mirrors the one in PVS or SPV, is a 90-degree angle, which we know because they are 2 halves that make a line. So they are 90 plus 90 equals 180, and therefore the angles are equal, and we already know that the sides are equal, so yes, the triangles are congruent. Part D asks, is angle QVP a right angle? Well, we already know that congruent supplementary angles would be 90 degrees. So since they are supplementary angles, which I said earlier, both of these angles here, 1, 2, equal 180 degrees. They look the same and they make a perfect 90-degree angle, which you already know. So they would be 90 degrees, equal 180. Number 5 asks that we construct a pentagon called penta, an equilateral triangle, and put them within a circle. And it has to have point O at the center. And we are asked to determine the measure of angle NOQ. So NOQ, we're asked to determine the measure of that angle. So first we need to know that the angle EOP is 72 degrees because it's the interior angle of the pentagon. And we can already see the angle EOP here is equal to angle EON here, which will just be good to know later on, the relationship between the 2. Angle QOP is 120 degrees, which we know by dividing 360 by 3, since the triangle splits the circle into 3 parts. And we can see the angle NOP is angles EOP and EON combined. So therefore, angle NOP, since angle EOP and EON are equal, would be 72 plus 72, or 144 degrees. And then we can see that the one we're looking for, angle NOQ, is equal to NOP minus QOP. So we have angle NOQ would be 144 degrees minus 120 degrees, which equals 24 degrees. And number 6 gives us this picture of a student. Her name is Jenny. She's about 1/4 of a mile from a cliff. She's holding a ruler 2 feet away from her face, and the cliff fits within a 1.5 inch span of the ruler. About how tall is the cliff is what we are asked. So first of all, we will use this relationship or equation here to determine the height or approximate height of the cliff. And we've got all of these different values in the word problem, but we're going to convert all of them to the feet unit of measurement. So 1 mile equals 5,280 feet. 1/4 of a mile would equal 1,320 feet. And then 1.5 inches equals 0.125 feet. So we plug all these values into our equation, and we get this, and then we multiply each side by 1,320, like so, and we find that the approximate height of the cliff is 83 feet. And that was the end of the lesson. Thank you so much for watching, and I hope you learned something.